We've built artificial intelligence with reasoning capabilities that rival human experts. Yet, the moment we ask these models to execute a multi-step task on their own, the system fractures into a chaotic loop of errors. This is the autonomy paradox. They can ace a bar exam or diagnose a rare disease, but if you leave them unattended to manage a real-world workflow, they fail completely. They forget their initial instructions, a phenomenon known as context drift. They hallucinate the names of tools they don't actually possess, or they get trapped trying the same broken command over and over again without realizing they're stuck. Treating an autonomous agent as a simple language model in a loop is a structural engineering flaw. To build a reliable agent, we have to surround the raw intelligence of the model with a rigid 4-layer systems architecture: logic, context, execution, and control. True agency does not naturally emerge from a clever text prompt. It is a strict software engineering discipline that has to be constructed from the ground up. The base of the stack is the logic layer. If the agent cannot reason reliably, everything else fails. And zero-shot prompting, simply giving the model a task and expecting an immediate answer, is mathematically insufficient for complex reasoning. We can quantify this failure rate. In January 2025, the International Journal of Innovative Research in Science, Engineering, and Technology published a comparative study analyzing how different prompting structures affect a model's reasoning capabilities. When a model is tested using a zero-shot approach, its accuracy caps at 60% for logical reasoning tasks. But when researchers baked structural constraints into the input, applying few-shot or chain-of-thought prompting, accuracy jumps to 80%. Chain-of-thought acts as a mechanical governor. It explicitly forces the model to articulate its step-by-step logic, mapping out how it intends to solve the problem before it is allowed to generate a final action. This 20% increase in accuracy secures the logic layer, preventing the agent from collapsing into the recursive error loops that characterize zero-shot failures. In early agent design, developers tried to solve the information problem by cramming every piece of domain knowledge, workflow rule, and tool instruction into a single massive system prompt. Injecting massive context up front overloads the model's attention mechanism. The agent begins to ignore earlier instructions, leading to forgotten rules and degraded performance over time. Advanced systems bypass this bottleneck. Anthropic's agent skills architecture operates the model inside a virtual machine with direct file system access, replacing the massive prompt with organized directories. These modular skills package instructions directly on the file system, eliminating repetitive baseline rules. This structure enables progressive disclosure, loading information only when required. The first stage relies on YAML front matter, which sits at the top of the skill file, containing just the name and description. Because only this lightweight metadata is loaded at startup, developers can install dozens of specialized skills without paying a heavy context penalty. The agent knows the tools exist, but it doesn't have to memorize how they work yet. The heavy procedural knowledge, the actual workflows and coding practices written in the body of the document, remains dormant. The agent only reads the full Markdown file when a specific user request triggers the need for that exact domain expertise. File system-based context transforms a general-purpose model into a specialized expert precisely when needed. Now that it knows how to do the work, it needs a way to physically execute it. An agent can possess perfect logic and perfectly managed context, but without a standardized way to interact with external systems, it remains trapped in an isolated sandbox. The execution layer solves this through the Model Context Protocol, or MCP. This protocol exposes modular toolsets like live search APIs, database access, and code execution environments directly to the agent. We can see this layer in action by looking at a real-world programmatic SEO project built using Claude Code and MCPs. In this deployment, the developer provided the agent with a targeted SEO strategy, 6 baseline Markdown templates, and access to external MCP tools like Firecrawl for web scraping and Perplexity for deep research. This initiates an autonomous execution loop. The agent analyzes instructions, formulates a tool call to a search API, and uses the returned JSON data to generate new code. It navigates through competitive analysis and research by repeatedly cycling through these tools without human intervention. The output is highly efficient. Working from just 6 base templates, the agent successfully extrapolated the initial parameters to generate 2,000 distinct targeted SEO pages entirely autonomously. This demonstrates the raw capability of the execution layer when properly connected to rigid logic and structured context. But exposing an AI to live web browsing and file manipulation introduces severe security risks. Full autonomy is dangerous. As agents gain the ability to write code, modify files, and browse the web, the attack surface for adversarial manipulation explodes. A single hallucination or misaligned objective could lead the agent to execute a destructive bash command or expose private user data, making purely autonomous deployment a high-risk liability. To secure the system, Microsoft Research developed Magnetic UI, an open-source framework designed to inject necessary human-in-the-loop oversight back into the agentic workflow. Their approach begins with co-planning. Before a single line of code is run, the human and the agent collaboratively map out the multi-step execution plan, ensuring the logic aligns with the user's intent. But the most critical safeguard in this control layer is the action guard, a strict programmatic intercept. If the agent attempts to trigger an irreversible tool call, the guard halts the execution flow entirely, demanding explicit human authorization before proceeding. Adding friction to the system doesn't defeat the purpose of automation. A structured human-in-the-loop framework is the only reliable way to extract productivity from imperfect systems without risking catastrophic failure. When we step back, the true shape of a functioning AI agent becomes clear. Chain of thought prompting secures the reasoning. YAML front matter optimizes the memory. The model context protocol provides physical capability, and action guards validate the safety. Developers can no longer treat large language models as magical, monolithic chat interfaces. High-performing, reliable agents are actually modular, file system-backed software networks. Autonomous AI shifts the human role within the development cycle. Instead of writing boilerplate code, the developer becomes a system architect and operational overseer.